First of all, it's important we look at arithmetic logic units as they stand. Arithmetic logic units are combinatorial digital circuits that perform integer arithmetic and logic bitwise. So when we mean integer arithmetic, we are trying to say that at the end of the day, the computer will be working on binary numbers. Integers, one of the primitives, whenever we talk about computer primitives, one of the computer primitives are the integer data type. So because we call them computer primitives, because when we dig as far as moving to the level of programming language, from the higher level language, the assembly language, and then the machine language, the machine language may ignore other type of data type, but cannot ignore its primitive. So we call it primitive from the word primitive, meaning it's as old as it boils down to the machine language. So what happens in the ALU is basically what happens in the ALU is integer arithmetic and bitwise arithmetic. Those integer arithmetics are usually the plus, minus, the division, and all those things you have, products and all of that under arithmetic. But on the logic, that's where we begin to look at not and or. I think we're going to expose all of this as we go on in the class. So a byte. What is a byte? It's important to know that a byte is common across all processors. A byte is 8 bits, but it is different processors have what they call combinations of bytes. So a byte means 8 bits generally. So when you have a byte into 4 places, which is 8 times 4, and that's 32 bits, or you can call them 4 bytes. Each processor decides to give this chunk of bits their various names. So we also made mention here that some registers can hold 8 bits and the byte, and some can hold 32 bits. So let's quickly move to what we have next. Okay, arithmetic logic units, ALU operations. Arithmetic logic unit, ALU operations. Now, looking at these are some arithmetic logic unit operations. You have plus f equal to a plus b. From what you can see there, f equals to a plus b. You have f equal to a minus b, f equal to a minus b minus 1. And you can see where you talk about the not a, the not b, the a plus 1. Remember, a and okay, thank you all for staying tuned in this video. Today we are going to be talking about arithmetic logic units, and then we're going to be talking about the operation, the circuitry operation that goes on the arithmetic logic units. Remember, according to the human model, the processor has the data processing part. It has also the control units, and all these parts integrate to work with the register and the buses so that the processor can communicate with other parts of the computer. So today particularly we want to look at the logic units, the arithmetic logic units, and what happens in the arithmetic logic units. So stay tuned while I take you through this. Okay. This is what we have today. Okay, trying to see. Okay, so the arithmetic logic units operations, that's what we intend to look at today. The arithmetic logic unit performs logical units performs logical units, and also performs bitwise operations. So today what we want to do is we want to consider the various operations performed by the arithmetic logic unit. For example, here we have f equals a plus b. F equals a plus b is a kind of operation. F equals a plus b, where f here is the output and a and b are bitwise or binary numbers. So these operations are various kinds of operations that could be operated, that could take place in the arithmetic logic. A, B, and F are registers, because registers. Now, last lesson we talked about this guy registers as memories in the CPU-based memories called registers. So these registers are used to load and store data in and out of the central processing unit. So now remember, the ALU is inside the CPU. So the registers are inside the CPU, not in the ALU, but they are there in the CPU to communicate with the CPU, to communicate with the ALU. So they send in your instructions to the the ALU works on them, and then also gives back the same outputs. Okay, now let's see how the ALU actually works. So we made mention of the arithmetic operation. These are the plus, minus, times. Talk about plus, minus, talk about times, which is the multiplication. Talk about division. So all these are operations under the ALU. Okay, now we want to look at ALU itself. What is this ALU of a guy? We've been hearing that the ALU is responsible for is a combinatorial circuit, electronic circuit responsible for carrying out all the logical and arithmetic operations that the computer does. How does the ALU do it? So we're going to look at that. We already said that this ALU takes in two inputs, at least an input, two input, because there are some inputs that are just single inputs that you have to negate. So at least one of the operands must be located in the register. As we move on, we are going to see what we mean by operand, what we mean by operand. So as we are going on, we are going to see about operand. Okay, now so let's just move to the ALU circuitry. Let's see the ALU circuitry. This is an ALU circuitry, and you see that this ALU circuitry has the control lines, and these control lines determines the operation. This is operation. So here you have the operation. The operation goes on here. So this is where you have the operation. So all your operation that goes on here. So you have addition is an operation, subtraction, and all of that. Even the XOR, the logical operation, they all go on there. So let's see. Let's see. Aside that, you also have two inputs. You have two inputs. Looking at the inputs here, so this is an input communicated from the register, and this is another input B. So and then this is the output. This is also a register. This is a register. It's a register. This is a register. So let's take note. This is just a register. This is also a register. This is also a register, and this is a register. So, or rather, you can call them information or data coming from the register, because we have to fetch them. So now let's look at an ALU operation in assembly language. A typical assembly language is this. Look at a typical assembly language. Add string 10. See, this is assembly language. Assembly language. This is assembly language. Okay, so this, what does this do? What does this do? This assembly language will take in it is going to read data from the string 10 register. String 10 is a nomenclature, it's a register nomenclature. And so, for example, look at this string here is used to identify a register in assembly language. It's used to identify a register in assembly language. It's used to identify a register. So this is a register address, and this is a register address, and also this is a register address. So now looking at this register, looking at this register, looking at this register, this says get what is in 10, the content of 10, register 10, the content of register 8, then add it up, add the content to uh, a register string 9. So now when you execute that line of code, I mean when you execute this line of code, what happens after you have executed this line here? Once you execute this line of code, look at what happens. The machine code translates into, that is, this is converted into a machine code. The machine code here is the hexadecimal form. Look at the hexadecimal form of this. This was written in a higher level language. It was written in a higher level language, and then it was translated into an hexadecimal, and this is also the machine code, that is the machine instruction of that that's the machine instruction, the zeros and one. This is binary, this is the binary form, this is the binary form, this is binary used to take zeros and one. So this is binary, and this is hexadecimal. So binary, and this is hexadecimal. The upper one is the hexadecimal. So binary and the hexadecimal. But these are conversions from this guy. All those two you see are conversion from this guy. This hexadecimal, and then this binary. So now you don't need to worry, this translation is made by the system, and so we're just trying to make you understand what goes on in the ALU. We're just trying to make you understand what goes on in the ALU. Now, from this code, I mean the binary code, this machine code, that is where the ALU reads the instruction of what the user means. After this decoding, the decoding will put them in machine instruction, and then it is now the responsibility of the ALU. It is now the responsibility of the ALU to get what this means. For example, the ALU decides to say, oh, this is 0, just starting, and then every of this machine code is divided into 4 parts. You see the operation. Where do you find the operation? Remember here, I made mention of where all the operation. This is operation. This is where you have the operation. This is where you have the operation. So you see from there, you can see list of operation. List of operation. Those are the list of operation. Add, subtract, and the rest of them. So this code here contains these 4 things: the operation, the operand, the first operand, which is this guy, the content of this guy, that's the first operand. The second operand, this is the second operand, the content of the second register. Then the destination of the results, that is this destination here. Look at it here, register 9. So it is this machine code, this code that is responsible during the decoding. The ALU decodes this machine instruction to knowing what the user meant by add string 10, string 8, string 9. That is how the ALU gets to do it. The ALU reads the machine instruction, the one in binaries, the zeros and one, and then it decodes it to know what the user meant. Let's progress, and we're going to get more. Remember, string 10 and 8 are inputs, they depict input from general purpose registers. So we are going to see what general purpose registers look like. Okay, look at general purpose registers. For the register number, we can see this is string 0, means this is a mnemonic for each of the register number. They are permanently 0, so you don't save anything here. You don't save anything here. Anything you save in that register would vanish, because the value of the content will always be 0. So whatever, when you save, you may feel it has executed, but it never stores there because the content of that register is permanently 0. Look at another register, register 1. This is assembler temporal, it is reserved. So reserved registers, you don't save anything there. Let me take you back to the previous slide. Observe that we are using register 10 and register 8, the content of register 10 and register 8. So when you move here, you see register 10 is between this place, this range. This is where you find the register 10. Okay, and that's also where you find register 8. They are temporary, not preserved across a function call. It means you can use them temporarily, they can hold data temporarily, but they are not preserved across a function call. So when you call a function, they lose their values. Okay, so and then if we go back again, we observe that we also have a string 9. All these strings are in this range of registers. So when programming assembly language, it's your duty to understand the kind of register you are loading from, the kind of register you are loading into, or the register you are storing information from to a memory. So these are register conventions, and I felt it was important we know them. Okay, so these are the 32 bits, 32 general purpose registers. These are general purpose, and they are 32. Of course, from 0 to 31 gives you 32. Look at this. Let's take a look at this. Let's take a look at this. From here, we notice something is going on here. This is an instruction. The instruction ORI, string 8, string 0, and 2. You see? So ORI is the instruction, string 8, string 0, and string 2. And here you also have ALU, string 10, string 8, string 9. Now, this is the current value of the PC. Remember in our last class, I told you about PC. PC is program counter. When you get into higher level language, you would only be seeing line numbers, but you will not see this PC. This PC is program counter, and it's a type of register in the CPU that tells the ALU to after execution of a line. For example, after executing this line, after executing this particular line, it is the duty of the PC to update this value to the next line. So how do you know the next line? The next line of instruction. How do you know the next line of instruction? You observe this is 0, this is 4, this is 8. The next one will be a C, because if you add 4 to 8 in hexadecimal, it's going to give you a C. So let's see. Considering this simple program, the program counter register are in brace brackets. These are the brace, all these here. Okay, the next line of instruction will be to add 4 to hexadecimal, to this hexadecimal. You add 4 to it, and it's going to give you a C. Now, in hexadecimal counting, I'll tell you why we get a C here. In hexadecimal counting, what we have is we have from 8, we move to 9. From 9, instead of moving to 10, we move to A. From A, we move to B. From B, we move to C. From C, we move to D. And then from D, we move to E. And finally, we move to F. So when you add 4 to this is 1, 2, 3, 4. So that's C. That's where you have this C. Well, we'll go into hexadecimals, we'll go into number systems. When we come fully into number systems and conversion from one number system to the other, we're going to come to understand this fully. Okay, now this is logic circuit. We already talked about this part before in our last lesson. Okay, we talked about this. So now we're going to look at logic gates. Logic gates are building blocks of digital circuits. Remember from beginning we told you a computer is an electronic machine. A computer is an electronic machine that accepts the computer is an electronic machine that accepts data and transforms this data into information. So today we're looking at logic gates as building blocks of these digital circuits. Now, we also said another way of representing digital circuits are using logic gates and truth tables too. We can use truth tables to represent logic gates and their function. So if you are not representing truth tables, if you are not using truth tables, you are using logic gates. If you are not using logic gates, you are using Boolean notations. So now let's look at the types of gates. There are majorly two types of gates: the basic and the derived. The basic, the derived. The basic gates. There are only three basic gates: the AND gate, the OR gate, and the NOT gate. So in the next, we will see what this gate looks like. These are Boolean representation of the gates and or not. These are basic. Then derived means they are gotten from combination of one or more of this one. So you have NAND, NOR, XOR, XNOR. All these are derived under logic gates. So these are types of logic gates or gates. You can call them logic gates or gates. Types of logic gates or gates. So these are types of logic gates or gates. So then let's see. Okay, these are Boolean algebra. Whenever we are talking about Boolean algebra, we are talking about algebra that has to do with, or the algebra that has to do with Boolean variables. Boolean variables. You know, when we talk about algebra in mathematics, we'll be looking at variables that have to come from the real number. You know, real number in mathematics, we're going to be looking at variables that come from real numbers or that comes from say integers. These are integers, mathematical notations of integers, so or natural numbers, Boolean. So but now this is Boolean algebra, meaning Boolean means it's either true or false. True or false, that's what you mean by a Boolean algebra. So it's either true or false value. So now from DeMorgan's theorem, here Morgan's theory has to do with helping us manipulate how we manipulate Boolean expressions or Boolean expressions. So one of the DeMorgan's law says that a NAND gate is equivalent. A NAND gate is equivalent. Let's go back. I would like to show you something from this. An AND gate is the same thing as, let's take an AND gate for A and B. The AND gate for A and B here will be A, B. Or you can write it is also equivalent to A dot B. That's AND gate. AND gate. That's the AND. So for the OR gates, it is A plus B. You can also say it's the same thing as A or B. This is A and B. Okay, so this is plus and this is dot, or you leave it like this. They are representation. So not here is we represent not as bar of A, and bar of A is equal to not A. Okay, so these are the basic Boolean. These are the basic Boolean, and then okay, so let's move to the next slide. I just wanted to point this out before we proceeded here. So, so this is DeMorgan's law. A NAND gate is equivalent to a negative OR. A negative OR. A NAND gate is equivalent to a negative OR, and a NOR gate is equivalent to a negative AND. So that's the DeMorgan's theorem, and that's what we have all here, and that's what we have all here. That this NAND gate, this, remember, this is AND gate. Let me go back again. I think I only showed you these are basic. These are basic. This basic A plus B, not A, is basic. Now let me show you for derive. Let me show you derive. So you see, NAND, pardon my pen, NAND equals not AND, not AND. Already we know the AND. We already know the AND here. So not AND, just to put this bar, okay? So we just start to put not AND. So sorry, this is just my pen. AND. So for the NOR, it is NOR is just not OR. NOR means not OR. Okay, so we just have NOR. NOR here means not OR. That is, if you have NOR A nor B, A, logic NOR B, the result gives you A or B not. So that's the NOR. So the XOR is an exclusive OR. It's an OR, but it is exclusive. So you have A XOR B. It will be A B exclusive, exclusive, single bar and not same bar. And same goes with XNOR. So XNOR, for the XNOR, it will be your NOR already, but exclusive plus B okay, so we'll get to see all of this as we proceed. So this is the DeMorgan's law. DeMorgan's law says NAND AB is the same thing as negative OR. So this is negative OR, negative OR. It's saying you can expand AB, can expand NAND AB to get not A plus not B. So this is one of the DeMorgan's law. That's what we have here. Okay, then it's saying what you have here. Then it's saying if we have A, B, the NAND, the negative, or when we have not A or B, it is the same thing as AB, not a product of or NAND of AB. So these are two major laws, and we'll be using them to simplify circuits as time goes on. This is identity. Identity is when you have two negative or two nots on a logical variable. It is going to give you, is equivalent to that variable itself. For example, if I have two negative or two NOT gates or two negative on C, or two negatives, let me put it well, make it a bit clear, two negatives on AC, the answer will become AC. So that's just illustration of some of the DeMorgan's. So we will look at the applications very much more later. This is just to label it. So now also when you have double variable, a variable multiplying itself, we are saying there's no need. It is identity plus identity. If they are identical, then it is just A. For example, CC is C, BB is B, AB is not A. But whenever they are the same, you can take them as one. Then this one says whenever you have a variable ending with a negative of that same variable, we are trying to say that they have cancelled each other. So the answer is 0. Is 0. This is 0. Okay. This is 0. So that's for this. That's for this guy here, negative 0. Okay. And then when you have a logical variable plus 0, it gives you 0. Okay. Now let's proceed and see the application of this. We're coming to truth table, and I've created these. This can stand as an exercise for us. Like, let's look at the following exercise. For example, this is how to draw a NAND gate. Complete the truth table and identify the Boolean expression for the logic gate. Now, I want to test your knowledge. This that looks like D. This gate looking like D is AND, but with the small round knot on it, it makes it NAND. So this is NAND. NAND, N-A-N-D. Please, don't mind my pen. So now let's see the truth table. This is what we call a truth table. A truth table shows how various combination of the binary numbers for those two inputs, how they give their respective outputs. That is how A and B combines to give, this final output here. So this place here is the output. Here is output. So that's output. Let me show you using my laser. This is the output. This is the output. These are two inputs, one output, two inputs, one output, two inputs, gates. This is the gate. This is the gate, and this is the output. Two input. This is the gate, and this is the output. Two input. This is the gate, and this is the output. The gate is the one that determines how those inputs combine to give you the various outputs. So since we are dealing with logical operation, we know that the possible numbers for these logical values, logical values would either be 0 or 1. So now the various combination in a truth table is, you say, this is how to form a truth table. You say 0, 0, 1, 1. This has repeated itself twice. This one repeated itself twice. Then the next one, it will repeat itself. 0 will now repeat itself once. 1 will repeat itself once. 0 will repeat itself once. And 1 will repeat itself once. So that's how we form this. If we have three inputs where we have A, B, C, and we have a NAND gate, if this is A, this is B, and this is, say, C, for example, and here is our output. So what we have here is the first set of combination, which is 0, 0, 0, 3 times, because we have three inputs. And here will now be, sorry, this is 4 inputs. 4 inputs. Here we have 2 inputs, because here you take this particular input here, you're having 4 here because you have 2 inputs. It's always 2, sorry, pardon me, it's always 2 raised to power n, the number of inputs. So for example, this is, if you have 2 inputs, then it will be 2 raised to power 2. If you have, this is number of inputs. So there are 2 inputs. That's why we have to repeat 0, 0 twice for 2 raised to power 2 inputs. And so we have 2 inputs because this is A, B. Unlike here, we have 3 inputs. And so we must fill up for 2 inputs. Here has to be 4. So you divide it. Let me show you something here. This is 2 raised to power 1. And this is 2. Oh, pardon my pen, please. This is 2 raised to power 1. And this is 2 raised to power 0. So 2 raised to power 1 is 2. So you repeat this you repeat 0 for 2 times, and you repeat the 1 for 2 times. So, but in this place, the number is decreasing as you move across the column till you get to 0. So in this case, let us do for that of 3 inputs. 3 inputs. Watch what I will do here. I'm going to move from, since there are 3 inputs, I'm going to begin from 2 raised to power. Here you are going to see I'm going to move from 2 raised to power 2, 2 raised to power 1, and then I'm going to move to 2. Oh, pardon my pen, please. I'm going to move to 2 raised to power of 0. So you see I'm decreasing as I move across the column. This is, sorry, this is one column, this is another column, and so here 2 raised to power 2 is 4. So I have to get 4 zeros, 1, 2, 3, 4. Then 1, 4, 2, 1, 1, 1, 1. So in 4 places. So use cleaner so that I can draw, get a perfect drawing. Okay, so here 2 raised to power 1 is 2. So I'm going to draw zeros and 1 2 times till I fill the column. 0, 0, 1, 1. So I'm going to use my eraser. 1, 1, 1. Then here again I repeat 0, 0, 1, 1. So for the next line, 2 raised to power 0 is 1. So I'll now do 0. I'll now do 0, 1, 0, 1, 0, 1, 0, 1. Okay, so just take a look by yourself so you see what I'm trying to do here. Okay, so I think you must have gotten the idea behind it. So let's fill this truth table. 0 times 0 is 0, because we have NAND here, so it means you should invert the 0 to 1. That is not 0. If it is not 0, it is 1. So not 0 is 1 and not 1 is 0. So now we're going to change here. Here is going to be 1. 0 times 1 is 0, of course. But because we are dealing with the NAND, we are going to invert the 0 to a 1. 1 times 0 is 0. But we are going to invert it to, because of the NAND, we're going to invert it to a 1. Because of this guy here. This guy is the one changing the result. This NAND there, the negative there is changing the result. Then 1 times 1 is 1. But because of the negative there, it flips it to 0. So this is OR gate, but with a NOT. So that's NOR. So this gate here is NOR, N-O-R. 0, 0, 0 plus 0 is 0, but because you are negating it, it becomes 1. 0 plus 1 is 1, but because you are negating it, it becomes 0. 1 plus 0 is 1, but because you are negating it, it becomes 0. 1 plus 1 is 1, but because you are negating it, it becomes 0. So here is just an AND. There is no there is no not there. It's just a direct and that's like multiplication. 0 times 0, 0, 0 times 1, 0, 1 times 0, 0, 1 times 1, 1. So I would leave this, okay, I would work on this and I'll leave you to work on the rest yourself. Okay, look at this one. Let's take a look at this. Take a look at this. See what's happening here. This is a NOT gate. So this is NOT. NOT means to just flip, invert. This is a NOT gate. Sorry, this is an AND gate. Is an AND gate. So this NOT gate is just to flip. You have only A here, so sorry, this is inconsequential. This is inconsequential, so and this is also inconsequential because for a single input, you just need to go to 2 raised to power 1. 2 raised to power 1. And the possible combinations in 2 raised to power 1 is 0 and 1. Sorry, 2 raised to power 0. So for one input, this is for one input. For one input, this input here, this A input here, sorry, got to use my cleaners. Apologies, please. So for one input, so here is just to flip the values. A, the output becomes 1, then for 1, the output becomes 0. So that's just it for that. So this is all. I'll give you the answer and I want you to fill the results. You can paste your answers in the comment section. This is all, and this is exclusive NOR. Exclusive NOR. So you look at that too. Okay, let's go to this. Let's move over. So I've given you that. That's a whole lot of assignment for you to fix the answers. Let's move to this. Write the Boolean expression for the logic gate. Write the Boolean expression for the logic gate. So this is AB, this is an OR gate. So this is Q will be equal to A, or the OR there is a plus, B. So that's the answer to that. So here is an AND gate. So this is just A, B. You can also write A dot B, but I prefer AB. This is a NOR gate. So it's just an OR gate that is inverted. OR gate of A and B that is inverted. Okay, then here this is a NAND gate, an AND gate that was negated, which is NAND. So it becomes A, B, AND of A and B that is negated. That's a NAND. So this is just a NOT gate. So NOT of only input A will give you bar A. Okay, so I'll leave this also for you. So you work on this. Let this become the assignment. Let me see what you can do with that. This should be your assignment. Write the Boolean expression for the logic gate. Okay, now let's see this. Draw a digital logic gate. Also, please, I would want you to do this. I want you to write the digital logic gate for this. I want you to write the Boolean expression for this. Okay, I'm going to write one, and I'm going to allow you write the rest. So let me write one, and then you write the other one. So this is an AND gate between A and B. So you have, first of all, you have, this is the final gate, and it's an AND gate. The final gate is an AND gate between the whole of this circuit, between the whole of this circuit. and this particular circuit. So and is the dot, and put and. So this is not D, not D, not D, and this side now. So in this other case, this is an OR gate. This is an OR gate. This is an OR gate. This one, an OR gate between this output, this side, between this one and this other one, which is just a C. So we are now going to look at this. Remember, see how we are breaking it down. So let's move. This moves. So this is the C. We started from the last, the output, till we got to the input. So now we look at this. This is an AND gate between A and B. So this is A, B, AND gate. Already OR is there. This OR already. Let me show you. This OR is there. Already got this OR. So that's plus C, and then we have the AND gate. This time I'll use it as dot. I mean this AND here, this one. I mean this AND gate here, this one. This particular AND here, I'm representing it with a dot here, okay? Because I'm about putting them in the expression. And then I now have A, D, not D. So that this logic circuits, you can decide to put this in a bracket. So this now becomes your final answer. So I would like to see this, you do this. I'd like to see you do this in the comment section. So we discuss. How about doing this? How do you go about with this? How do you go about with this? I would do this, and I would leave you to do this. So let's see. It's about the last exercise, brace up. So here, what is the major AND joining? First of all, you have to split the operation into two parts. So this is one part, and this is another part. So it means the major or the final output there, the final output should be an OR gate. Please pardon me, my pen. OR gate. So the OR gate is between two inputs. So this is one input and this is another input. So this input is for the AB, and the AB is connected to a NAND and an AND that has two inputs. The second input has a NOT to it. Please, sorry, I'm going to use my eraser. It has a NOT to it. I already taught you about NOT before. Small circle here. Okay. So this is the B, and this is the A. This is a NOT gate, please take note. This is NOT gate. And so this is C. There is also an AND gate here. The bracket means an AND gate. Sorry, I'm going to use my eraser. Okay, and so these two gates, let me bring it out for clarity's sake, though they are supposed to be on the same line. This, let's bring it out, doesn't mean. So here is a not C, so series is would create a not. Okay, so let's create this, let's get this more clearer to avoid some confusion. And so this is your C, and then you have to create your A and B. So this is OR. Take note, this is OR. So that OR is now your A and B. This is your A and B. Now, I'm going to tell you something. You see that these are different inputs from this A and B. So it means that the circuit is not correct. It means that this circuit is not correct because we cannot have different A's and different B's. So rather, what we would do is this. Watch. Get this off. Get this off. Let's see what happens here. Get an AND. Okay. This is an OR. So you can tap. Let's see. Eraser. Can tap an A or B. This is your A. You can tap from your B here. Let's go back. Sorry. Eraser. So already have this OR between A and B here. Take it here. Then I get myself a negated C here. Okay, so that's the circuit. That is the circuit. But you see, in circuit design, we could still break this down using DeMorgan's theory. Could still use DeMorgan's theory to break that down. So that's a problem we'll be setting up in our next class. So use DeMorgan's theorem to break it down. So but this is what the circuit looks like, and so I would like you to do this. I would like you to draw this. It's up for you. If you want to really know how to do this, you take a grasp and get it done. Okay, so thank you very much for being part of this class, and I hope to communicate in the next I hope to communicate in the next class. So thank you all. Thank you very much.